Okay, thank you. Okay, I want to thank the organizers for inviting me to come. And I want to thank you all for coming here. And I also want to say the slides are already on the web. So if you want to follow along and maybe look back at a slide I went by too fast, feel free to do that. Well, if you want to check your email, I won't know. So anyway, this is the third talk I've given on this topic, although I've tried not to make them duplicate the style of presentation too much. So you might also want to watch these two earlier videos if you're interested in what I'm talking about today, and I've got links to them there. So let me address an issue that arose today. What are combinatorial interpretations good for? Well, one thing they're good for is if you find 100 or more combinatorial interpretations for a certain integer sequence, you get to write a book about it. And if you find 1,000 or more, you get to found a journal about it. Okay? But if you've already got a good combinatorial interpretation for a number, why would you want another one, and then another one, and then another one? Okay? It helps you find new open questions, and isn't that why we're here? Okay? Let me give you 3 examples. Alternating sign matrices. Okay? There is a way to turn an alternating sign matrix into a nice combinatorial picture, these osculating paths. But there's another thing you can do that turns them into 2 factors of graphs. It's a trivial transformation that turns the one into the other. But if you have a 2-factor of a graph, you get to ask questions about how the points on the boundary are joined up to other points on the boundary. And in the case of alternating sign matrices, you find this really bizarre symmetry relation, this dihedral symmetry of the link pattern associated with these fully packed loops, something you would not have been able to find if you were just satisfied with your original supply of combinatorial interpretations. Yes. Not so germane for this talk, but it's a subgraph in which every vertex belongs to exactly 2 edges, except maybe the ones on the boundary. But if you look at my article on interpretations of alternating sign matrices, the many faces of alternating sign matrices, I hope there in that article I show you how having a rich supply of different ways to look at a combinatorial object really gives you a lot of explanatory power, and also is a source of open problems. Another example is downsets of a pose set, trivially equivalent to upsets of a pose set, trivially equivalent to independent sets in a pose set. But if you take the natural bijections between the first, the second and the third, and the first and the third, you find you have a non-trivial map from a set to itself. And this is row motion on a pose set, something you wouldn't have necessarily been able to find unless you had all 3 of these sets and these really almost trivial bijections between them. Third example, alternating sign matrices, the descending plane partitions, totally symmetric self-complementary plane partitions. That's too many combinatorial interpretations, but now you have a fun problem, which is try to show that they're in some sort of bijection with each other. So again, having multiple combinatorial interpretations can give you lots of fun problems to work on. So that, I think, is a rationale for finding combinatorial interpretations for things. Now, speaking of alternating sign matrices, they have been a source of pain, at least for David Robbins, who said, these conjectures about alternating sign matrices are of such compelling simplicity that it is hard to understand how any mathematician can bear the pain of living without understanding why they are true. Okay? So it is not my goal to inflict pain today, but I do want to give you some maybe not quite comfortable itches and make you feel like, wow, there really ought to be a way to solve these problems. So I'm going to introduce some new ideas and also some open problems, some of which are half open, one half open from the left, another half open from the right. You'll see what I mean by that in a little bit. Okay, some terminology. If you know graph theory, you already know what a dimer is. You just don't necessarily know that word. It's an edge. That's all that it is. A dimer is an edge of a graph. And a dimer cover is what we'd call a perfect matching of a graph. Specifically, it's a set of edges with the property that every vertex in the graph belongs to exactly one of your selected edges. And the main problem that I'm going to be launching off from is the question, how many dimer covers does a certain finite graph have? These are often related to tiling problems. So here is a dimer cover of a 4x4 grid graph. I've shown the selected edges in red. I can surround the two vertices that share a red edge by a 1x2 rectangle. And if I then get rid of the non-selected edges and the selected edges, you can see I've tiled the region with dominoes. And I can reverse the process. Starting from a domino tiling, I can go back to a perfect matching. Here's another example. This is a sort of a honeycomb graph you get by cutting out from the infinite honeycomb grid a finite hexagonal region. Here's a perfect matching of it. We can surround each one of those selected edges with a rhombus, also called a lozenge, also called a calisson. And then we can erase the edges, and what you see is a lozenge tiling of a hexagon. And again, all those steps are reversible. So there are some beautiful formulas counting the number of such perfect matchings, aka dimer packings of graphs. So for the 2n by 2n square, the number of perfect matchings or domino tilings is given by this curious double product. The factors are not integers, but somehow when you multiply them together, you do in fact get an integer. McMahon found a formula slightly different from this for the number of lozenge tilings of a regular hexagon, and McDonald reformulated as this elegant triple product. Again, the factors are not integers, but if you multiply them all out, it turns out to be an integer. And I want to point out, for reasons that will become clear later, that this number is really smooth, by which I mean it's a product of primes that are much, much smaller than it. More specifically, this number is exponential in n squared, but its largest prime factor is at most 3n, in fact, less than 3n. So we'll see more numbers like that later. But when you see numbers like this, you think, something is going on, because most numbers do not factor into small prime factors. But here's an even more extreme example of a smooth number. This is the number of domino tilings of an Aztec diamond, which is just a power of the smallest prime there is. And this result is a bit later than these results, because it's not always obvious what the right shape to try to tile is, or what the right subgraph of some nice infinite regular graph you want to restrict to if you're trying to find a nice formula for the number of dimer covers. Now, there's a general method which takes all problems about perfect matchings of planar graphs and reduces them to another problem, namely computing a determinant. And this is the permanent determinant method, or if you've got a non-bipartite graph on the next slide, you'll see what that's called. Temperley and Fisher, and independently Castellane in the early 60s, gave a general method for counting perfect matchings of planar graphs. Specifically, they showed that if you take the adjacency matrix of the graph, its permanent is going to be the square of the number of perfect matchings of the graph, but computing permanence is hard, so that's not really useful. But if you fiddle with the entries of the adjacency matrix, okay, there's my first mistake. Let me just write down the mistake, because it should be the square of the number of perfect matchings. If you take the adjacency matrix and replace some of those ones by minus ones, then suddenly the problem of computing a permanent is replaced by the problem of computing a determinant, which is much easier. Sometimes you might want to use actual roots of unity other than 1 and minus 1 in your matrix to make things work out nicely. If your graph is planar, but not bipartite, there's a variant of this trick called the Pfaffian-Hafnian method. And here's an example of the kind of class of problems you can apply this method to. Not a bipartite graph, but it has perfect matchings, and you can count them by evaluating a Pfaffian. Any questions so far? Yeah, question in the back. I believe the Hofnian is just an unsigned version of the Pfaffian. So is there a general formula for counting trimer covers of finite planar graphs? Not a rhetorical question. Do any of you know of one? I haven't seen one. I'm sorry? Oh, yes, a trimer would be a set of 3 vertices. But you're right, there's some ambiguity there. Do they have to be all connected mutually by edges? Or is it enough that they be connected in some fashion? That's right. So under the most liberal definition of what this question could mean, does anyone know of an affirmative answer that might be relevant to my questions? Maybe I should ask this question after my talk is over, when you see what kinds of applications I have in mind, and you can tell me if you know of any tools that might be applicable. So I don't know the answer to the first question. Are there nice formulas counting trimer covers of some particular graphs, sort of analogous to the problems of counting domino tilings of Aztec diamonds, et cetera? I'm pretty sure the answer is yes. I say pretty sure because I haven't proved the formulas are true, but as is usually the case in enumerative combinatorics, when you find a pattern, usually it's not the universe thumbing its nose at you. Sometimes it is, but usually there's something there. So I'm going to restrict attention to tripartite graphs, and I'm going to require a trimer to contain 1 vertex in each color class. And I'm not going to require that all 3 of the vertices be connected to each other in the underlying graph, just that they form a connected subgraph. The induced subgraph should be connected. So you could have U goes to V goes to W without having an edge between U and W. So I want to comment on what got me into looking at tilings in the first place a long time ago, which were a couple of articles written around 1990 by John Conway and Conway-Lagarias, and a follow-up article by Bill Thurston, which talked about how you can solve certain kinds of tilability problems, not enumerative problems, but questions of the form, can you tile this shape with tiles of this kind, using combinatorial group theory, if you're Conway-Lagarias, or using a combinatorial topology, if you're Bill Thurston. Actually, each of them used both approaches. Slight difference of emphasis, but same basic idea. And the specific kind of problems they looked at were tilings in the hexagonal grid, which has a natural 3 coloring. And you look at tiles that can be formed by looking at 3 hexagons, which either form the shape on the left, down there, yeah, this kind of shape where they're all mutually adjacent, or this kind of shape on the right, where they're consecutively connected to each other. There's some confusion terminologically in the literature because Conway and Thurston called the one on the right a tribone, and Stanley and Ardila, and also the online encyclopedia of integer sequences called the one on the left a tribone. So I'll avoid using the word tribone and use my own terminology. I'm going to call the one on the right a bone and the one on the left a stone. Now, as in the case of dimer configurations, dimer packings, there's a duality going on. So if you take the center of each hexagon and replace it by a vertex, then you can see that tilings of the kind that Conway and Lagarias and Thurston studied are equivalent to filling up a graph.
In your pockets, I guess.
Is there a question?
Okay.
Oh, okay. Thank you. Is there anything on the chat coming in? Okay. So it's dual to pictures that look like the picture on the right, where you've got 3 dots in a row connected by a line, or 3 dots forming a nice compact little triangle. So that's the game. Now, it's not hard to show that if you've got one of these sort of honeycomb triangles, like I've shown here, with n equals 5, n hexagons on a side forming a triangle denoted by T sub n, you can tile it with stones and bones if and only if n is congruent to 0 or 2 mod 3. In one direction, that's easy because if n is 1 mod 3, the number of hexagons is not even divisible by 3. So you certainly can't tile it with triples of hexagons. But if we're doing combinatorial enumeration, we can say, well, how many ways can you do it? So David Desjardins wrote a computer program that can count tiling problems of a fairly general kind. And I ran it on this problem, and I got some numbers that I don't really know what to do with. They're not in the OEIS. If you give them to superseeker, it shrugs. If you ask people who know a lot of integer sequences, they say, I don't know. So it's not clear to me what's going on here. In fact, there is something interesting about this sequence, but I won't tell you what until fairly late in the talk. Yes, Alex. No, they do not factor nicely. They have, well, let me be more careful in my answer. They have big prime factors and small ones, but they've got some big ones. But I haven't told you yet what really impressed me about these two articles. What impressed me is they brought this new idea into the study of tilings using combinatorial group theory. So using non-commutative groups to get an interesting way to look at these problems. Yes, Vic.
Question in the chat. There are 3 color configurations on bones. Are we allowed to use all of them or just the?
Great question. Are we allowed to use all the kinds of colored bones? And the answer is yes. So we're allowed to use any coloring of the stones, any coloring of the bones. Bones come in 3 orientations, stones come in 2. Anything goes at this point. Later on, I'll restrict things a bit, but for now, that's the rule. David.
I think if I were counting those, one variant I want to try is weighting them like 3 to the number of stones. Stone is a bone, bone is an event.
So I love David's suggestion. This is exactly what I wanted to have happen. This is why I gave this talk. We've already got an idea for a variant of this problem that we can try. So David's suggestion is do a weighting where each stone counts with a weight factor of 3. So the weight of the tiling as a whole is 3 to the power of the number of stones, because you can think of a stone as being kind of a bent version of a bone, if I've caught that idea correctly. Yeah, that might lead to something really nice. I don't think David's program will do, oh, actually, no, it will. If you give it 3 copies of a tile, it treats them as different. So in fact, there's a kludgy way I could get his program to do that. So maybe by tomorrow morning, I'll have a chance to run that and I'll let you know if I find anything interesting. Thank you. Okay. So anyway, I'd love to give a whole talk just about these 2 papers, but this is supposed to be about open problems. So I'm not going to, but I urge you to acquaint yourself with this beautiful idea of Conway and Lagarias and Thurston. What they use it for is to show that in certain cases you cannot do the tiling at all. So the first theorem I've listed there is that Tn can be tiled by stones if and only if n is congruent to 0, 2, 9, or 11 mod 12. We know it has to be 0 or 2 mod 3, but this is a stronger condition that has to hold. And the second theorem is that T sub n can't be tiled by bones alone for any n bigger than 0. You cannot do it for any n. So I want to say a little bit about what this invariant is. One way to compute it is with this complicated calculation involving the boundary word of the region being tiled. I won't talk about that here, although in the last talk I gave at the Rutgers Colloquium, I talked about that a little bit. But here's one way you can compute it. If you tile the region with a mixture of stones and bones, look at the number of rightward pointing stones minus the number of leftward pointing stones for that particular tiling. That turns out not to depend on the tiling. All the tilings of that region will give you that same value, okay? And this is one way you can prove that a region can't be tiled by bones alone, is if you can construct a tiling in which the number of leftward and rightward pointing stones are unequal. So when n is in one of those 4 congruence classes mod 12, you can do the tiling. So you can count them. So here's the sequence showing the number of ways to do it. Again, I've left out the zeros, but again, I don't really see a pattern here. There are large prime factors. OEIS doesn't recognize it. Superseeker doesn't recognize it. So It's not clear what to do with this problem. So what do we do? Well, if Philippe were here, he would tell us, try domain wall boundary conditions, okay? What are domain wall boundary conditions? That's not a rhetorical question. They use the term in the physics literature in a way that makes it unclear whether they have a specific meaning in mind or they want the term to retain a certain, shall we say, flexibility to it. Over the years, I've acquired a certain grudging respect for the different ways physicists think and communicate. I think the idea, and those of you who know the physics literature maybe will correct me if you think I have it wrong. I think the way a physicist thinks is, well, we don't really know what the term should mean yet. So let's use it in a kind of loose way until maybe later on we'll figure out what the right definition is. So I think what mathematicians could use for those who are touring the domain of physics is some sort of tour guide that would tell us how to understand what it is that we're reading, okay? Or maybe what's really needed is a self-help book written for both sides of the divide, telling us how to talk to each other, okay? Anyway, following my idea of what a domain wall boundary condition is, which may not be other people's, I came up with these shapes called benzels, which seem to have the desired property of giving rise to at least conjectural nice enumerations. One way to think about them is they're kind of analogous to Aztec diamonds. So if you have a large square, you have lots of freedom near the boundary about how you lay those tiles. Near the corners of an Aztec diamond, things are very tightly constrained. Benzels are designed to have that same feature near the boundary. If you want to know more, you can watch the video of the talk I gave back in November of last year. So here's an example of a benzel. They always have 120-degree rotational symmetry. They form a two-parameter family. Here I'm denoting the parameters by A and B. And A and B can't be too far apart. Each of them is bounded by 2 less than twice the other. Here's the 5, 7 benzel, and you'll see it's tiled by bones alone. Okay, nothing else, no stones there. What is a benzel? Well, let's build the 4, 6 benzel. So I'm going to have these spider arms. This is sort of a 6-legged spider of these jagged legs coming out, alternating in length in the honeycomb grid from a center point with length 6, 4, 6, 4, 6, 4. Okay. I'm going to fit a hexagon around them whose sides alternate in length between 2 numbers. And then I'm going to look at all the hexagons inside that hexagon, all the little unit hexagonal cells inside that big non-regular hexagon. And that's the 4, 6 benzel for you. I've tiled that, and you will notice that all the tiles in that tiling are stones, and that all the stones are pointing the same way. Well, that tells you something. It tells you, given the Conway-Lagarias invariant, that you really can't do anything else other than have a tiling in which all those tiles are pointing the same way. In fact, it's not hard to get from there that it has only one tiling. I believe, but have not yet proved, open problem alert, that the AB benzel can be tiled by stones alone exactly when A plus B is 1 mod 3. Okay, audience participation time. I showed you that the 5, 7 benzel can be tiled just using bones, those 3 hexagons in a line tile. Seems to be kind of an outlier because if you take A and B between 1 and 10, that's the only case, 5, 7 and 7, 5, where you can tile using just bones and no stones. But there is another one. Can anyone who has not heard me give this talk before or have another source of insider information hazard a guess as to what would be the next pair of values A, B for which you can tile the AB benzel with bones alone? 1014, that is incorrect. 12, 15 is the next one. Okay. Anyone have a guess what the next one would be? 22, 26 is correct. That's right. So what's the pattern? Pentagonal numbers. That's absolutely correct. These are pentagonal numbers. So here's a theorem from a couple of months ago. The AB benzyl can be tiled by bones alone only if A and B are paired pentagonal numbers, K times 3K plus or minus 1 over 2. Here's a sketch of the proof. First, compute the Conway-Lagarias invariant. There are actually 3 cases according to the residue of A plus B mod 3. Second, rule out 2 of those 3 congruence classes and show that the only feasible case is where A plus B is 0 mod 3, in which case the invariant takes the value A plus B minus 3A squared plus 6AB minus 3B squared over 6. Set that invariant equal to 0, since there are no stones of either direction in the tiling. Solve for B in terms of A, show that 24B plus 1 must be a perfect square, and then check that this only happens when A and B are paired pentagonal numbers. Okay? So does anyone notice what's missing from this slide? Actually tripped over the words a little bit. Yeah, if and only if. I started to say if and only if. I believe that that's true. Computer evidence shows that it's true, but I can't prove that it's true. Okay, that's a half-open problem. Show that a certain quantity is at least 1. Okay, so there appear to be lots of such tilings. In fact, the number of them seems to grow exponentially in K to the 4th power. Okay, which is basically the area. That's kind of what you'd expect for a tiling model with some positive entropy, is it should scale like an exponential in the area. So there appear to be lots of them, but I don't know how to construct any of them systematically. Anyway, you're going to help me. Maybe, I hope. Question? None. It's just a snazzy title. Yeah. I'm sorry, repeat the question is there any connection with Euler's pentagonal number theorem? Maybe the optimistic way to phrase the answer is not that I know of, and maybe you'll find one, but I see no reason to expect that there would be one. I mean, like Fibonacci numbers and Catalan numbers, pentagonal numbers, you know, have a name because they turn up a lot. So they might have just turned up in this case for no reason at all. Anyway, outside that door, to your left as you go out, or up here if you come down at the end, you will find these 2-sided sheets of paper with benzel graphs on them. Okay, this one's not too big, this one's a bit bigger. If you really want, I've got the next one, but remember the number of tiles you're going to need to draw grows quartically in the parameter, so it's going to be really big. It'll fit on a page, but you'll have to squint at it to do it. Anyway, what you could do is basically try to construct one of these 3 things in a line, tilings or covers of these regions, and see if you can do it in a systematic way which you think will scale for all values of K. And if you can find a way that does that, please let me know, because that would give a way to prove that there's always at least one way to do this. Okay? Yeah, crowdsourcing, exactly. So some of them are down here, some of them are up there. So here's what you're going to do. You'll take a picture that looks like this into a picture that looks like that. Okay? I advise you to use a pencil and not a pen, unless you're very brave.
Do you have that PDF in your slides for the audience at home?
Oh, this. No, I do not. I probably should. So maybe I should add that to the talk before. Yeah, let me, that's slide 50. Yep, and the PDF I'll also put in the next one. Okay. Here's an alternative approach to showing that that number is positive, the number of those tilings. Can you prove that every benzyl has a stones and bones tiling in which all the stones point the same way? If you could do that, then for a region in which the Conway-Lagarias invariant is known to be 0, then as long as you've shown that at least one tiling exists that's not constrained to have no stones, you'd be able to sort of cancel off the stones by this kind of argument and be left with a tiling with no stones at all. So that would be another approach. So now let's put some constraints on. I have not tried constraining things by color at all. As you'll see, there are plenty of things to fill the hour, even without considering other kinds of constraints. I'm just going to look at constraints where there are these 5 kinds of tiles. There's 2 orientations of stones, there's 3 orientations of bones. So that's 2 to the 5th power, different subsets of the tiles, and I'm including the empty set because it's just simpler to include that. But in fact, you can mod out by symmetry. And it turns out if you mod out those different tiling problems by symmetry, all you need to know is the number of stones you're allowing, 0, 1, or 2, and the number of bones you're allowing, 0, 1, 2, or 3. Turns out that up to symmetry, you don't have to worry. And the reason is because stones have this 3-fold rotational symmetry and bones have a 2-fold rotational symmetry. So turns out you just need to know those 2 numbers. So what if you allow 1 kind of stone and 2 kinds of bones? I'm not going to discuss cases where you have so few tiles you can't do it at all. So here's a picture of what you get. So you'll notice that there's a kind of a widening wedge from the origin, which is sort of the, oh, actually not in this case. In this case, the non-zero numbers are all clustered really closely to the diagonal. Anyone recognize those numbers? Double factorials, that's right. So here's a conjecture. When A and B both equal 3n, or when one of them is 3n plus 1, and the other is 3n plus 2, the number of tilings of the AB benzel with 2 kinds of bones and 1 kind of stone, fixed, I should say. You have to hold them fixed. So fix in advance which orientations of stones and bones you want. Then the number of tilings is going to be given by this double factorial 2 times 4 times ... times 2n. Newsflash from a few weeks ago, this problem is now half open, because Ben Young has shown that the number of tilings is at least this double factorial. So your job is to prove that there aren't any more, to prove that the number of missing tilings that Ben didn't find is at most 0. Okay? So it's half open from the other side. What if we allow 2 kinds of stones and 2 kinds of bones? Okay. Here's a table. And this has the sort of wedge thing where for A and B, actually, I should probably not even show those ones outside that wedge, because there A and B do not satisfy those inequalities. What really happens when A and B go outside that range is your hexagonal benzel degenerates to a triangle, and it's not changing shape as A or B moves around in that region, because you're basically cutting off half planes that are already cut off, so you're not losing anything new. So you should probably ignore those ones on the outside. But inside this wedge of pairs A and B that satisfy those 2 inequalities, you have some interesting numbers. So one thing you could do is you could look along the boundary of that wedge where A is nearly twice B, or B is nearly twice A. And there you find that the number of tilings appears to grow exponentially in the area. Sorry, exponentially in the length dimension, exponentially in the square root of the area. So it's kind of like a 1-dimensional thing disguised as a 2-dimensional thing. Yes? The ones that are in the wedge. I believe those are just the tilings that have only bones in them. Sorry, only stones in them. But I have not checked. So that's my guess. So hiding along one of these nearly extremal diagonals where you're on the boundary of that region satisfying inequalities, you'll find the Schroeder numbers, the large Schroeder numbers. And hiding along a parallel diagonal are some closely related numbers, which are in fact the very next sequence in the OEIS. But the real action is close to the diagonal, because there you're really seeing a number of configurations that's exponential in the area rather than the square root of the area. So those are the really interesting and big numbers. Here's some examples of 4 diagonals from inside near the main diagonal. I don't have an exact formula for most of them, but for one of them, I do have a conjectural exact formula, but all of them have the same signal indicating that there should be a nice product formula. Namely, even though they grow exponentially in n squared, the largest prime factor of the nth term grows only linearly with n. In this case, is bounded by 4n. So David Desjardins figured out one of the product formulas empirically. To figure out the other 3, we'll need to know more terms. At some point, David's program just doesn't isn't able to handle the problem. So finding a better program that would give us more terms might enable us to formulate conjectures that we don't have yet. What if you allow everything? So both kinds of stones, all three kinds of bones, anything goes, what happens? Well, now, unfortunately, there are no conjectural product formulas. You don't have small prime factors anymore. But there's an interesting, intriguing clue that there is something to be said. And this is this two-adic continuity phenomenon, which sort of comes out of left field. So if you look at the numbers, if you look at the number of tilings where A is equal to n and B is equal to 2n minus 3, this, by the way, is sort of near the boundary again of that feasible region. So it's not really along the main diagonal where the most entropy lives, but it's still interesting. If you look at these numbers, the number of tilings goes, well, mod 2, it's always even. That calls for explanation. Mod 4, it's always 2. Mod 8, it alternates between 2 and 6. And the data suggest that the residues mod 2 to the k are periodic mod 2 to the j for some j, which is another way of saying that that sequence is two-adically continuous relative to the two-adic way of measuring distance. And the same is true when a equals n and b equals 2n minus 4. So why should that kind of phenomenon hold? Where might two-adic continuity come from? Well, I know of just one proved example of two-adic continuity in the tilings literature, and that's a result of Henry Cohn. Let T of n be the number of domino tilings of a 2n by 2n square. As one of the earlier speakers remarked, you can write this as 2 to the n times the square of s of n, where s of n is the number of domino tilings of the nth Pactor half square. So Henry Cohn showed that the sequence s of n is two-adically continuous. And how did he do it? He used the exact product formula that you get for the number of tilings of a 2n by 2n square and the related product formula for the number of tilings of Pactor's region. But for us, we don't have a product formula. So that only explanation that I can think of for why there'd be this kind of two-adic continuity isn't available. So there are many ways to interpret this, but one of them is maybe there is a product formula. Maybe it's like the product formula for the number of perfect matchings of a 2n by 2n square, which is sort of disguised because you don't see small prime factors, but there's still a nice formula there. So maybe here too, there's some nice product formula. I should also say that there are other two-adic properties of tiling problems. I have a preprint called Some Two-Adic Conjectures Concerning Polyomino Tilings of Aztec Diamonds. Here's one of the pictures from there. And there are a couple of examples from that paper of situations where a certain combinatorial quantity, depending on n, appears to be two-adically continuous as a function of n. So there may be some larger story here about two-adic continuity and maybe exact formulas for some of these quantities. In fact, let's go back and look at that original sequence that I showed you that I said was so unpromising. If you look at all the tilings of the honeycomb triangle by stones, and if you look at the multiplicity of 2 in the factorizations of the non-zero terms, slowly drifting upward. Now, this is really 4 sequences interspersed with each other, because remember, there were 4 congruence classes mod 12, which is where things are going to happen. So you'd really want to look at those 4 separately, and I don't have enough data here. But my conjecture is that the number of tilings goes to 0 two-adically, and there may even be a nice exact formula for the exponent of the prime 2, even if other primes don't do anything systematic. I also want to talk about mutations, because there's this fact that if you have any domino tiling of a simply connected region, you can mutate it into any other domino tiling by way of these tatami moves that take a 2 by 2 square tiled by dominoes and rotate it by 90 degrees. Also, if you have a lozenge tiling of a simply connected region, you can get from any such tiling to any other by means of these rotations of a hexagon that's got 3 lozenges in it. So is there something similar true for these kinds of problems? So here's an open problem. It's been around a while, actually. Can every stones and bones tiling of a simply connected honeycomb region be obtained from every other tiling of that region by a sequence of 2 flips, each of which replaces 2 tiles by 2 other tiles. Or I should say trimers, I guess, since I'm in the trimer picture here. So one thing you can do is take this kind of a picture, which has, so these pictures, I forgot to rotate by 90 degrees, sorry. But anyway, in this kind of grid, you can have, I would have said a leftward and a rightward pointing trimer. Here, they're upward and downward pointing. So just rotate everything by 90 degrees. But you can retile that by sort of allowing those 2 trimers to cancel. Or you can have a triangle with 3 dots on a side, and you can cover it in a different way by moving the small triangle and having a different bone coming in to fill up the remaining part. So it is not known whether you can always do this. Wait, sorry. But if it were true, it would yield an alternative proof of the invariance of the Conway-Lagarias invariant, because it's easy to check that for all these pictures, which by the way are to be understood as allowing all the different rotations to happen too. So there's a lot more moves than this. Yes, there's a question, Greg.
Yeah, so for the bottom picture, why do you also not put to the place bottom?
You absolutely can. So I'm intending these to be prototypes of moves, but where you can take any one of these moves and rotate it. So the move you described could be obtained from rotating this move. It doesn't have to be involutive. You could define the moves to be involutions. You totally could. Anyway, you can check that each of those moves preserves the invariant. So that would be one way to prove that the invariant is an invariant. Intriguingly, Scott Sheffield has shown that if you throw out one of the 3 orientations of bones and just look at tilings using both orientations of stones, but only 2 of the 3 orientations of bones, within that class of tilings, these mutations suffice. But if you allow all 3 orientations of bones, then his method of proof doesn't work. So that's a great open problem. I would love to see someone solve that. Wait, there was supposed to be another slide in here. Oh well. Anyway, let me talk a little bit about random tilings, because one of the things that I looked at pretty early was random tilings and Arctic Circle phenomena and stuff like that. It'd be really interesting to know for these trimer models whether they're analogous phenomena, and you'd expect there to be, because there's this kind of stiffness along the boundary, this rigidity. You don't have a lot of freedom near the boundary. This is exactly what's responsible for these sort of Arctic Circle phenomena for dimer models. So we would expect there to be something like that for this case too. And in fact, a very simple experiment I did is I looked at a specific location along the boundary, and I counted the number of tilings of the region you get when you remove a tile, a trimer of this kind or this kind of this kind. And I found that one of them was really predominant. So the vicinity of the boundary really wants to be tiled in a particular way based on this one admittedly isolated experiment. So I really do believe there are going to be sort of frozen regions near the boundary. Question? Define for a while. Okay, that's a fair answer. So yeah, if you start to see nice pictures and the nice pictures qualitatively stabilize, that's a good estimate of the mixing time for the Markov chain. But a priori, it's often hard to figure out how long will be long enough. So that would be a good strategy, actually, is just to try it and see how long it appears to take. If you really want to be unbiased and don't want to trust a Markov chain to mix in a reasonable amount of time, one thing you can do is just use this counting program as a kind of a subroutine where you ask yourself, well, what's the probability of this particular tile appearing in this particular place near the boundary? And if you can look at all the different ways a particular little hexagonal cell can be covered by a tile along the boundary, which are mutually exclusive and jointly exhaustive, then you can figure out how to design a little die that you can roll with a random number generator on your computer to tell you which of those tiles to place. Now, the complement of that tile that you've placed gives you a smaller region. Lather, rinse, repeat. Just keep on pulling away tiles from the boundary. And what you get will be as good an estimation of what a random tiling would look like as your quasi-random or pseudo-random number generator is at generating things that act as if they were random. So that's what I call the brute force way. And it would be very informative, but I'm not a good enough coder to do that. So one of the reasons I'm giving this talk is that many of you like to code. Many of you are better at it than I am. So anyone who thinks this is a fun project or wants to get involved, one great thing that I really need would be coding that would actually let us determine things like, what are the probabilities of specific tiles being in one of these tilings? What would a random tiling look like? So please see me if that interests you. I should say, in addition to coders, also people who are good at algorithms. For example, another thing that would be great is if you could use some sort of height function for this model to do something like a monotone coupling from the past, that would be fantastic. I don't know how to do that, but that's sort of a theoretical question that would pay off very big for this model, but might also have other benefits as well. What about proving the conjectures? Okay. Well, one idea that I'm very fond of is including more variables. Give me a Q, Q, give me a T, T. What have you got? Still not enough variables. Okay. Greg is still wearing, are you still wearing, where were you sitting, Greg? Greg Musiker, are you wearing your Somos t-shirt? Yeah, Somos sequences. So when I wanted to find a combinatorial interpretation of Somos numbers, my strategy was to insert more and more variables into the Somos recurrence until finally I ended up not with numbers, but polynomials in which every coefficient was 1. What do you have then? Then you have a whole bunch of monomials whose patterns of exponents are kind of an encoding of a combinatorial object. So that's one way you can get to combinatorics through algebra, is inserting more variables, which is more of an art than a science, but try and do it in a way that's sensitive to the recurrence or to whatever you're doing so you can actually pull something out. It's not necessarily trivial to turn a pattern of exponents in one of these Grove polynomials into a beautiful picture like Grove. So I'm not pretending that finding these polynomial refinements is the end of the story. There's still what's really going on with these exponents, but it's a large part of the way towards finding a combinatorial interpretation of things. Another thing one could do to approach a problem like this is read Baxter. I mean, this is how Greg Kuperberg found his proof of the alternating sign matrix conjecture, is actually going into the physics literature, actually reading Karapin and Izergin and stuff like that, and finding their methods and saying, I can use this, okay? Or maybe you want to read Gelfand, Kapranov, and Zelevinsky and learn about hyperdeterminants. Because a priori, I mean, if you're taking a determinant of like a 3-dimensional matrix, that sounds a little bit like trimers, right? So maybe there's a way to apply that. Here's an approach which I don't know how to follow through on, but what if you could forget about determinants somehow, selectively? Put yourself in the frame of mind where you don't know anything about determinants, but you know about dimers, okay? And you somehow work backwards from dimers to reconstruct the theory of determinants. I mean, I've used Castellane's method for decades, but I think of it still as a trick. I don't think of it as something necessary and fundamental. And I think that's a limitation in my understanding. I think if you could really understand why the permanent determinant method must work, starting from dimers and saying the way certain things transform must correspond to, oh, these are things that multiply like matrices, then maybe having done that process, you could then go back to trimers where you don't have to try to forget what the algebra is that supports them because it hasn't been invented yet, then maybe you could invent it. So that's a thought about how you might approach this problem. I want to end with something fun and simple, which you'll be able to do and get a good feeling before dinner, which is to solve this easy counting problem. Form a honeycomb parallelogram with 3 hexagons on its short sides and n hexagons on its long sides. We're going to forbid bones that are parallel to the long sides of the parallelogram, but allow the other 4 types of tiles. So here's a typical shape of the kind that I mean. And note that I'm not allowing vertical bones. I'm only allowing bones in the other 2 orientations, but I'm allowing both kinds of stones. How many tilings are there? There's a nice answer, and you should be able to find a nice combinatorial proof of it. So that's all I got. Thanks for listening.
Thanks, James, for a beautiful talk. Are there any questions?
Yes.
You mentioned this phenomenon of two-added continuity occurring in one example, but also conjecturally in this other one. Is there any two-added continuity for other primes in your situation?
For those 2 situations, there is not. Oh, sorry, thank you. Yeah, the question is, what about larger primes, primes larger than 2? Do you have 3-added continuity? Do you have 5-added continuity? I did a little experiment where I downloaded the entire OEIS to my laptop, and I sort of looked for p-adic continuity phenomena. And there are lots of sequences that do, in fact, have p-adic continuity for all primes. For instance, polynomial sequences, which are in there, and certain other sequences also. But if you sort of sieve out those, then 2-adic continuity seems to dominate over 3- and 5-adic continuity. So there's something going on there. So then I sieved out for sequences that satisfy linear recurrence relations, because some of those satisfy 2-adic continuity for somewhat elementary reasons. But I was still left with 10,000 sequences in the OAIS that satisfy 2-adic continuity. So that's 10,000 open problems in combinatorics, trying to come up with maybe some uniform way of explaining why these sequences would have this kind of continuity property. And I just don't know what's going on. I know there were other hands. Yes.
Where does benzel come from?
Okay. So benzel, Gustav Benzel was the inventor of the merry-go-round. So the name is suggestive of sort of rotary motion. Benzene has these hexagons. The Mercedes-Benz logo has this nice 120-degree angle. But mostly, I really like the word benzel, which I got from a Carl Sagan science fiction novel called Contact. So I think part of me was always on the lookout for a way to introduce this word into the mathematical lexicon. And here I found my excuse. Yeah. You know, I could barely hear you, but it occurs to me, maybe I should bring the mic to the person who's speaking so that I'm going to be Phil Donahue or something. I'm going to just, okay. Thank you.
So maybe I'll summarize. What's with the small prime factors? What's your intuition?
I think it means there's a product formula analogous to the one for lozenge tilings of hexagons. And in one case, David Desjardins did find an exact conjectural product formula, which has the desired feature that it would explain why there are small prime factors, because the individual numbers are rational numbers where the numerator and denominator are linear functions of the indices I and j. So working backwards, if there are small prime factors, you think there's a product formula in the other cases as well. That's what I think it means. Does that answer your question?
Yes, thanks.
Sure.
Do we have a question there? James?
So what are the numbers for the benzels again?
What are the numbers?
Yeah, like in the little examples.
Oh, no, there's the 1215 on one side, and there's the 2226 on the other side. Sure. There was a question down here. Can I meet you in the middle?
So I was just going to ask your first strategy. Do you mean something like the octahedron recurrence for timers of Aztec diamonds, like some similar things like that are enumerated by these trimers?
Well, ultimately, that would be beautiful to find something like that. But I think the way to start is just by assigning different variables to different positions that a given tile can have and see if there are some nice patterns governing that. But I don't see why there would be a kind of octahedron style of occurrence, but that would be my dream, that the story of these tilings would be as analogous as possible to the things I already know about. Yeah, sure.
All right, well, James is still there. Any questions?
Any questions on this side of the room before I move to the other aisle?
All right, I guess that's all the questions. And thank James again.
Thank you.